In this video, I'll be going over the graphs of logarithmic functions. So what we see here first is the graph. Well, we have f of x over here, which is an exponential function. And over here we have g of x equals log base 2 of x. And how the exponential function, the graph of the exponential function and the log function, because those functions are inverses of each other, the graphs are reflected across the line y equals x. So sometimes we may use an exponential function to give us an idea of what the log function looks like. And in this video, we'll talk through the different characteristics of log functions and how the transformations work. So down here are some of the characteristics that we want to keep in mind. This function is 1 to 1. And again, I'm looking at the highlighted g of x up here. So that graph is 1 to 1. These graphs have vertical asymptotes. So the vertical asymptote of g of x is going to be the y-axis here. So similar to the way that an exponential function has a horizontal axis or a horizontal asymptote, the log function has a vertical asymptote. There are the domain and range. There's no y-intercept unless we have a transformation. The x-intercept is 1, 0. And then we are increasing if the b value, so if that base value is greater than 1. And then if it's between 0 and 1, it'll be decreasing. And we'll see examples of all of these things. So let's just graph a basic log function, log base 1/5 of x, plot 2 points on the graph, state the domain, range, and asymptote. Okay, so this is in the form log base b of x. Okay, so because of that, that is going to have the same shape and characteristics pretty much of everything that we had up here. So there's no transformations on this one. So a couple ways that we can do this. Probably the best way is to write this as an exponential function, or we could write this as 1/5 raised to the f of x is equal to x here. So swapping this out as a log or an exponential function. So 1/5 is the base raised to the f of x is equal to x. Now what I'm going to do is I'm just going to make a table of values. Okay, so in this equation though, I'm going to first choose f of x values, raise 1/5 to that value, and then that'll give me the x coordinate. So 1/5, the easiest value to pick is 0. 1/5 to the 0 is 1. 1/5 to the first is 1/5. So there are two coordinates that are going to go on the graph. And again, just like we saw up here, we have an x-intercept of 1, 0 right here. And then I have 1/5, 1. So something like there. This is going to be, it's kind of hard to get a smooth curve on this, but it's going to look, let me do that part again. Something like that. Okay. And then we want to find the domain, the range, and the vertical asymptote. So the domain here is 0 to infinity. The range is all real numbers. And the vertical asymptote is x equals 0. This is the y-axis. Okay, so if you recall how the graphs or how the domain, range, and asymptote worked for an exponential function, these are kind of flipped from what was happening with an exponential function. Okay, so that is the most basic graph of a log function that we could have. And what's happening as the base changes here, that is just, so any other fraction, anything that's between 0 and 1 will be decreasing, so similar shape as this. If it's, if the fraction is something like 1/10 or 1/100th, that second point, this point right here, is just going to move more to the left. So 1/10 or 1/100th or 1/1000th will move left. If it's 1/2 or 1/2, I guess that'll move to the right. If that base number is between 1 and infinity, then, or just greater than 1, it's going to be an increasing function in a similar way that second point will change. All right, so we can have all of the types of transformations that we've seen for our other functions here. And first, let's talk about a vertical shift. So vertical shift is going to be a value outside here. So adding a constant or subtracting a constant will move this function up or down. Okay, so on this first one, b f of x is our parent function. If I'm adding a constant d, that's just going to shift this up. And then if I'm subtracting a value d, that's just going to shift this down. Okay. For a horizontal shift, these shifts are occurring inside the argument. So I'm going to add c or subtract c. If I add c, that's going to shift this function to the right. If I subtract c, sorry, I have that backwards. If I add c, that's going to move it to the left like this. If I subtract c, that's going to move the function to the right. And notice that the vertical asymptote changes when I do that shifting, that left and right shifting. All right, so let's go ahead and graph this function, log base 4 of x minus 3 plus 2. So how I like to think about this first is f of x log base 4 of x, which is, that's the parent function for this particular function. And actually, I'm not going to call it f of x. Let's call it g of x. Okay, so if I transform this to an exponential function, that's going to be 4 to the g of x is equal to x like this. And then let's make a table of values. Okay, so I'm going to input some values for g of x. And again, the easiest values are 0 and 1. When I say 4 to the 0 power, well, that's 1. 4 to the first power, that's 4. So I'm going to go ahead and graph this g of x function first. So 1, 0, and then 4, 1. I have a vertical asymptote of 0. Not a very smooth curve, but you get the idea. So that's g of x. And then all I'm going to do is I'm going to identify what the shifts are. So this means I'm going to shift right 3 units, and then this means up 2 units. Right 3 is an x, a change to the x coordinate. Up 2 is a change to the y coordinate. So I'm going to come up with what the new coordinates are on that function. Okay, so if my first coordinate is 1, 0, and I'm going to shift right 3 units, that means the x coordinate is going to get added 3 values to that. So 1 plus 3 is 4. The y coordinate does not shift. And then 4, 1. Oh, I'm sorry. Both that y coordinate does shift. Both coordinates are going to shift because we have a horizontal shift and a vertical shift. So once again, x, we're going to add 3 to that value, and then we're going to add 2 to the output value, or f of x in this case. So that'll be 4, 2. And then 4 plus 3 is 7. 1 plus 2 is 3. So these are the new coordinates for that shifted function. So I'll go ahead and plot those. So here, and then here. Now, originally, the vertical asymptote was x equals 0. Since I'm shifting right 3, the new vertical asymptote is x equals 3. So we usually want to start out by graphing the vertical asymptote. And then this curve just gets close to that. Then like that. So something like that is the new f of x graph. And this isn't always what you need to do, but I always suggest graphing the parent function first and then the transformed function. So we've plotted 2 key points. We could label those. This graph is kind of small, but we kind of have the points over here. So the domain here, well, I'm going from 3 to infinity. The range for a log function is always all real numbers. And then what is it asking us for? The asymptote. So the vertical asymptote is x is equal to 3. All right, let's look at some of the other transformations we could see for a log graph. We could stretch or compress this. That corresponds to the leading coefficient. So if the leading coefficient is greater than 1, we're going to have a vertical stretch. Okay, so this is a stretch by a factor of a in this case. And then here on the second graph, because the coefficient is 1 over a, something less than 1, we're going to compress this. So this is a compression. And all the y coordinates of each point are going to be multiplied by 1 over a. Okay, and then graphing reflections, we could have 2 types of reflections. If I have a negative in front of the function, that's a reflection across the x-axis, so that's a vertical reflection. That's what's happening here. If I have a negative inside the function, that's a reflection across the y-axis, which is what happens here. Okay, so I think there's just a couple things left in this video for us to look at, a couple of examples. And here's a summary of all these transformations that we've talked about. All right, looking at this example, let the parent function for each of the transformed functions be f of x equals log base 4 of x. So this is the parent function. It's not on the graph. But what we want to do is we want to find a function for a, b, and c here. So So A, B, and C. Okay. I apologize if you're colorblind. All right, so A, well, first of all, let's discuss what this parent function looks like. So since the base value is greater than 1, this is going to be an increasing function. Since there's no transformations, I have a vertical asymptote at x equals 0. And then this is going to go like this. If I wanted to, we know that the x-intercept is 1. If I wanted to find the second point, you could say 4 to the f of x is equal to x. When f of x is 1, I get an x value of 4. So it's going to be 4 here, 1 here. So this point is 4, 1. Okay, so thinking about that the graph of that parent function, let's see how things are going to change to get these transformed functions. So looking at A, it looks like I originally had, or the new graph for A has an x-intercept of -1. So if I originally had an x-intercept of 1 and it's now -1, looks like it's the same shape. The vertical asymptote was, so let's just kind of spell this out here. So the x-intercept, what is going on here? So the x-intercept is now -1, 0. That means the new vertical asymptote is x equals -1. And it's the same shape as what we had in our parent graph. So this looks like we're just shifting to the left 2 units. So we're going to say log base 4 of x. We're going left, so we'll say plus 2. And I'm going to call that, well, it's just a. So I'm not going to write it as an equation. So log base 4 of x plus 2. All right, so for the next one, for b, well, we're still going to use a base of 4, even though we're decreasing. So the way that this can become decreasing is by having a reflection. And there may be a way we could do either a vertical or... No, we're only going to do a horizontal reflection. This is going to reflect across the y-axis. So if I reflect this across the y-axis, it's going to be like this. And then I want to move it to the right 2 units so that I still have that same x-intercept. So this is going to be log base 4. And I'm subtracting here. And then I'm moving this right, so I'm going to put plus 2. But we want to take out that negative sign. So I'm going to write it as log base 4 of negative x plus 2 is how we want to write this. Reflecting, and then we're adding 2. So that second way is how we'll write that. Okay. Some of these are a little tricky. It's sometimes tricky when we have 2 horizontal shifts or 2 vertical shifts together. It's not always clear which one comes first when we're applying them. So my suggestion would always be to pick some points to actually test to make sure your transformations are correct. And then lastly, for C, this looks a lot like the parent function, just with a reflection vertically. No, I'm sorry, I was looking at the wrong graph. We're looking at C here. So this looks like we're just shifted left 2 units and have a vertical reflection. So we're going to say negative log of x plus 2 here. So we're shifting left, and then we're having that vertical reflection, which is what that negative sign is in front. All right, and then one last example. Graph the function g of x equals 3 ln x minus 9 plus 1 on the same axis as its parent function. State the domain, range, intercepts, and asymptotes of g of x. Okay, so we'll say f of x is the parent function. And that's just going to be ln of x, which means, remember, log base e of x. Okay, so if I wanted to graph ln of x, that is going to be an increasing function because e is greater than 1. This is an increasing function going through 1. And a second point that's going to go through, let's check this out. So we would say e to the f of x is equal to x. When x is, or when f of x is 0, x is 1. That's the point I've graphed. And then when f of x is 1, I get e, which is about 2.718. So 1, 2, maybe something like right there. Okay, so I have 1 comma 0, and then e comma 1 as my second point. All right, so let's look at the transformations that are happening. This 9 means right 9 units. And I'm actually going to make a small change because I want to make sure that everything shows up on the graph. So let's say instead of 9 there, let's change this to minus 5. Okay, so we're going right 5 units. We're going up 1. And then this is a vertical stretch by 3. Factor of 3. Okay, so we're we're going to have x and g of x. So what we need to do here is, let's see. Well, I'm just going to take those points that we have, and I'm going to apply those shifts. So if I'm going right by 5, that's going to change the x coordinate. I'm going to add 5 to it. So that 1 is going to become a 6. And then I'm going up 1. So from 0 plus 1 is 1. And then I'm going to do a vertical stretch. Well, actually, I'm going to do a vertical stretch by a factor of 3 first, and then I'm going to add 1. So vertical stretch by a factor of 3 means I'm going to multiply this 0 by 3. So 0 times 3 is just 0 still, and then up 1. So I'm going to have 6 comma 1 here. And then moving down, e plus 5. So it's going to be e plus 5 as my second x coordinate. And then for the 1, vertical stretch by a factor of 3. So 1 times 3 is 3, and then add 1 is 4. So this is going to be a little bit tricky to plot these points, just because e plus 5 is, not it's not a whole number. It's not going to be one of the intersecting points on the graph, but we can do our best. 1, 2, 3, 4, 5, 6, 1. There's that point, 6, 1. Then e plus 5, that's going to be about 7.718. So here, 1, 2, 3, right, something like that. So it's a little bit steeper of a graph. Before, the vertical asymptote was x equals 0. On this new graph, the vertical asymptote is going to be x. I'm moving it over 5, so x equals 5 is the new vertical asymptote. Right here. So my graph, something like that. So it's a little steeper, and that's what it's going to look like. Okay, so the domain for this graph is from 5 to infinity. The range is going to be all real numbers, and then the vertical asymptote is going to be x is equal to 5 here. One thing to mention, which this question doesn't ask, but let's find what that x-intercept is. All right, so how we're going to do that is, let's take the original function, which is g of x up here, and to find the x-intercept, I make g of x 0. So we're going to say 0 is equal to 3 ln x minus 5 plus 1. And so to find the x-intercept, I have to solve this for x. So I'm going to subtract 1 and divide by 3. And that is going to allow me to convert this to an exponential function. So the base is e, so this is e to the negative 1/3 is equal to the argument. Add 5 to both sides. So 5 plus e to the negative 1/3 is that x value right there. And I don't know what e to the negative 1/3 is. I don't have a calculator handy, but it's going to be 5 plus a small number. And that makes sense and corresponds to what we see on our graph. So the x-intercept, and it's actually fine to keep it this way, e to the negative 1/3 is the same as 1 over e to the 1/3. That's the x-coordinate, and then the y-coordinate is 0. And you know, this is an exact value, which is always preferable. But in this case, when we're graphing, it's sometimes good to get a decimal, but you could type that into your calculator to evaluate that.